Hello everyone, thank you for joining me. This is the D-Wave 2 Quantum Computer Technology Overview. This is a PDF I downloaded. Talks a little bit about what the D-Wave is there, but what I want to get to is the quantum computing right here. Speed computation, quantum computers tap directly into an unimaginably vast fabric of reality. The strange and counterintuitive world of quantum mechanics, rather than store information using bits represented by zeros or ones as conventional computers do, quantum computers use quantum bits or qubits to encode information as zeros, ones, or both simultaneously. This superposition of states, along with the quantum effects of entanglement and quantum tunneling, enable quantum computers to consider and manipulate many combinations of bits simultaneously. The D-Wave 2 processes with 1,000 qubits can evaluate all 2 to the 1,000 possible solutions at the same time. The D-Wave 2 system implements a quantum annealing algorithm which solves problems by searching for the global minimum of a function. This is fundamentally different from the familiar framework of classical computing built on logical operations, but is always relevant in many high-value problems such as minimizing error in a voice recognition system, controlling risk in a financial portfolio, or reducing loss in an electrical grid. While there are different ways in which users can submit problems to the system, at the level of the machine instruction of the quantum processor, the system solves a quadratic, unconstrained binary optimization problem, QUBO, where binary variables are mapped to qubits and correlations between variables are mapped to couplings between qubits. The system of interacting qubits is evolved quantum mechanically via the annealing algorithm to find optimal or near optimal solutions. Solving problems with the D-Wave 2X system can be thought of as trying to find the lowest point on a landscape of peaks and valleys. Every possible solution is mapped to coordinates on the landscape, and the altitude the landscape is the energy or cost of the solution at that point. The aim is to find the lowest point or points on the map and read the coordinates, as this gives the lowest energy or optimal solution to the problem. The special properties of quantum physics, such as quantum tunneling, allow the quantum computer to explore this landscape in ways that have never been before possible with classical systems. Quantum tunneling is like a layer of water that covers the entire landscape. As well as running over the surface, water can tunnel through mountains as it looks for the lowest valley. The water is an analogy for the probability that a given solution will be returned. When the quantum computations occur, the water, or probability, is pulled around the lowest valleys. The more water in a valley, the higher the probability of that solution being returned. A classical computer, on the other hand, is like a single traveler exploring the surface of a landscape one point at a time. The D-Wave 2 is colder than interstellar space. Reducing the temperature of the quantum processor to near absolute zero is required to isolate it from its surroundings so that it can behave quantum mechanically in a general that performance increases as temperature is lowered. The lower the temperature, the better. The D-Wave 2 processor operates at a temperature of 15 millikelvin, which is approximately 180 times colder than interstellar space. The refrigeration system used to cool the processor is known as a dry dilution refrigerator. It uses liquid helium in a closed loop cycle in which it is recycled and recondensed using a pulse tube cryocooler. Closed-loop refrigeration removes the need for on-site replenishment of liquid helium and makes the system suitable for remote deployment. Despite the extreme environment inside the system, the D-Wave quantum computer can be located in a standard data center environment. Protein folding is one application of these quantum computers. Simulating the folding of proteins could lead to a radical transformation of our understanding of complex biological systems and our ability to design powerful new drugs. This application looks into how to use a quantum computer to explore the possible folding configurations of these interesting molecules. With an astronomical number of possible structural arrangements, protein folding is an enormously complex computational problem. Scientific research indicates that nature optimizes the amino acid sequences to create the most stable protein, which correlates well to the search for the lowest energy solutions. With researchers at Harvard, we designed a system for predicting the folding patterns for lattice protein folding models and successfully ran small protein folding problems in hardware. Machine learning. When you look at a photograph, it is very easy for you to pick out the different objects in the image. Trees, mountains, velociraptors, etc. This task is almost effortless for humans, but it is in fact a hugely difficult task for computers to achieve. This is because programmers don't know how to define the essence of a tree in computer code. Machine learning is the most successful approach to solving this problem, by which programmers write algorithms that automatically learn to recognize the essence of objects by detecting recurring patterns in huge amounts of data. Because of the amount of data involved in this process and the immense number of potential combinations of data elements, this is very computational expensive optimization problem. As with other optimization problems, these can be mapped to the native ability of the D-Wave processor. Object detection. Quantum hardware trained using a binary classification algorithm is able to detect whether or not an image contains a car. Together with researchers at Google, we built software for determining whether or not there is a car in an image using a binary classification algorithm run in hardware. In excess of 500,000 discrete optimization problems were solved during the learning phase, with Google developers accessing the D-Wave system remotely. Now this I found really interesting, the Monte Carlo simulation. Many things in the world are uncertain and governed by the rules of probability. We have in our heads a model of how things will turn out in the future, and the better our model is, the better we are at predicting the future. We can also build computer models to try and capture the statistics of reality. These tend to be very complicated, involving a huge number of variables. In order to check to see if a computer statistical model represents reality, we need to be able to draw samples from it and check that the statistics of our model match the statistics of real-world data. Monte Carlo simulation, which relies on repeated random sampling to approximate the probability of certain outcomes, is an approach used in many industries such as finance, energy, manufacturing, engineering, oil and gas, and the environment. For a complex model with many different variables, this is a difficult task to do quickly. Okay, this is a video, Changing the World, Vern Barnwell, CEO, D-Wave Systems Incorporated.
And at first I thought, wow, this sounds like science fiction. I had never, I had heard of quantum computing, certainly, and read about it in journals and so on, but I had no idea that anybody had built a commercial product. So it just seemed fairly out there to me. And so I really didn't believe the recruiter and kind of let it go, but she was fairly persistent, called me back, suggested that I talk to a couple of the board members, and I had a phone call with actually one of the board members that I knew. And the more I learned, the more interesting it got. And what really sort of sealed it for me was actually coming out here to Burnaby, a suburb of Vancouver, and meeting this team here. They're just an awesome team. They're earnest, some of the best people in the world for this particular project. They had really accomplished what I think is nearly a miracle to get this far and to do this against all odds. I mean, many people had told them over the years that it was impossible and nobody could do this. But Jordy and the other founders really had an incredible vision, and it had come to fruition by the time I had gotten here. So I don't have much contribution to what's actually been done here, but nonetheless, I was fortunate enough to join them about 2 years ago and help them with the commercialization of the product and bringing the product into the hands of customers and things like that, and continuing to fund the company. And it's just been the greatest experience of my life, or my career certainly. And I think I told you once that I had spent a lot of time at Goldman when I ran technology for Goldman, seeing different ideas come by, various investors or companies with new products would come by and say, well, what do you think about this as a practitioner in IT for a global investment bank like Goldman? What do you think? And I saw a lot of great technology in those years that I was there. I was there 11 years, but I'd never seen anything that has the potential to change the world like this does. It's I believe one of the handful of milestones in the history of computing that we'll look back on is this company, and I am so glad to be part of this and so proud of this team. It's just, it's, as I said, it's been the greatest experience of my career.
The computers that will change the world and have. Thank you all for watching and subscribing. Have a great night.